Page 16 of Complex Numbers and Polynomials. Page 197 reading. The Fundamental Theorem of Algebra by Gauss again. This happened to be his PhD dissertation. Every polynomial of degree n is greater than or equal to 1 has at least one zero, which can be written in the form a plus bi, where a and b are real numbers. Now notice that either a or b could be 0, so it doesn't mean that they have imaginary roots necessarily. It could have an imaginary root, but they might be real too. Okay, if b is 0, then a plus bi is a real number. So it doesn't say that it's necessarily complex, but it might be. If p of x is a polynomial of degree n, then p of x has exactly n zeros, some of which may be either irrational numbers or complex numbers. Okay, so basically, if you have a polynomial that has a higher degree, then the number of zeros that that polynomial will have will be n zeros. Okay, and now we return to the first one. It says if a polynomial has a degree of n is greater than or equal to 1, has at least one zero. And then so in b, we can see that not only is it at least one zero, but for every degree that you have, like if you have an x to the fifth polynomial, then that means you have 5 zeros. Okay? For real polynomials, and what that means is a real polynomial has coefficients that are real. It doesn't mean that the roots are real. For every real polynomial of degree n can be factorized into n complex linear factors, some of which may be repeated. Okay, that kind of goes along with what it says up here, right? We said that a polynomial of degree n has n zeros, and basically this is also saying that it has n zeros, which are complex, okay, and some may be repeated. Every real polynomial can be expressed as a product of real linear and real irreducible quadratic factors where discriminant is less than 0. Okay, so if you want to reduce it into linear factors, then some of the zeros are going to be complex. But if you're allowed to combine some of the linear factors together, then you'll be able to express the real polynomial in factors of linear and quadratic factors. Okay, so what that means is that, okay, so you have a real polynomial. The real polynomial has real coefficients, okay, real number, it says this is bad notation, but okay, you have all real coefficients. You can factor this into linear factors like that, or like that, or you could factor into quadratics, which also have all real coefficients. Now, if you say that you want to factor this completely into linear factors, then some of the roots are going to be complex. But if you're allowed to combine some of the complex roots, pairs, they're conjugate pairs, right, into quadratics, then you could express this into factored form where all of the factors are either linear or quadratic with real coefficients. And maybe that doesn't mean anything now, but we'll figure out what that means, okay? And the quadratics that you express it in, the discriminant, of course, is going to be less than 0 because the roots are complex. Every real polynomial of degree n has exactly n zeros, some of which may be repeated, okay? If p plus qi, where q is not equal to 0, is a 0 of the polynomial, then its complex conjugate p minus qi is also 0, okay? Every real polynomial of odd degree has at least one real 0. Okay, so we just read that if there is a complex root, then that means that the conjugate of that root is also a root. So complex roots always come in pairs if the polynomial has real coefficients. Okay, and so then they say, okay, if you have an odd number as far as the degree of the polynomial, like x to the fifth or something, that means that you have to have at least one real 0 because the complex zeros come in pairs. So if they come in pairs and you have 5 roots, then one of the roots is kind of left over. Okay? So let me give you an example. Let's say that you have an x to the fifth polynomial, blah, 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 and it has some roots, and the roots it has are like 1 plus 3i and 2 minus I. So if it has these two complex roots, you know that the conjugate pairs are also roots because it says that up here, right? And so these are 4 roots right there, 2 pairs, 2 conjugate pairs. And so there's a fifth root because this is x to the fifth. There must be a fifth root. The fifth root obviously can't be a complex number because then where's the space for the complex conjugate, right? So the fifth root must be a real number. Okay, that's all the last one was saying. Let's move on. Okay, find all real polynomials of degree 3 with zeros, -1/2 and 1 minus 3i. So if it's a real polynomial, which means it has real coefficients, that of degree 3, that means it's going to have 3 roots. And if it's going to have 3 roots and 2 of them are here and here, we know that the complex conjugate pair of this complex root must also be a root because otherwise the coefficients can't be real. So even though they only told us 2 of the roots, we know from the facts that it's a real polynomial that there's a third root, which is 1 plus 3i. Okay, so if we want to find all the polynomials that have these roots, then we would say, okay, it would be coefficient a, unknown, and multiply times x minus -1/2, which is the linear factor. And then there's going to be 2 complex linear factors, which are going to be x minus 1 minus 3i and x minus 1 plus 3i, right? Now let's simplify this a little bit. The linear factor is going to be x plus 1/2, the real one. And then here, let's say we're going to have x squared minus, and then we're just going to square, or we're not going to square, but we're going to multiply those two together, right? So 1 minus 3i times 1 plus 3i would be 1 squared plus 3 squared. And what do the middle terms look like? So -1 minus 3i times x, -1 plus 3i times x. So the imaginary parts cancel out, the real parts combine. So -1x minus 1x is minus 2x. Okay, so we're going to have x squared minus 2x plus 10. And we'll have x plus 1/2 times a. And if we want to, we could multiply that out. But even the book doesn't multiply that out, so you could just leave it like that, okay? Let's look at number 3. 2 minus 3i is a 0 of this polynomial where p and q are real. Okay, again, a real polynomial with real coefficients. Using conjugate pairs, find p and q and the other 2 zeros. Okay, so if we know that the coefficients of this polynomial are real, and we do because it says that p and q are real, and 1, of course, is also real, then we know that not only is 2 minus 3i a root, but 2 plus 3i is a root, okay? Because complex roots occur in conjugate pairs if the polynomial is real. So let's try to find out what p of x is going to be, okay? So let's say the first factor of p of z is going to be z minus 2 minus 3i, and the second factor is going to be z plus 2 minus 3i. And then we're going to expand this, and it's going to be z squared, and the last term is going to be, I'm sorry, I did that wrong. It's z minus 2 plus 3i, okay? So if you multiply the two last terms together, you'll get 2 squared plus 3 squared. And the middle terms would be the complex terms will cancel each other out, and you're left with minus 2z and minus 2z, which would be minus 4z. Okay, and so basically we have z squared minus 4z plus, and this would be 4 plus 9, which would be 13. So, and how did I know that there's no a term here? Okay, how did I know there's no a term? Because it's 1z cubed, so I know that there's no, the a equals 1 if there is an a term. It's just 1. Okay, so I know that the two known roots are 2 minus 3i and 2 plus 3i, and then we still need to find one other 0 to figure out what is the p and q here. Okay, and so let's say that the unknown 0 is known as, let's say, b. And then let's figure out what b has to be. Okay, so we could use lattice multiplication, or we could use the book method, which is it writes the coefficients of this polynomial, and underneath it writes the coefficients of this polynomial. So I'd have something like that. And so that would be negative 13b plus 4b minus b, and this would be 13, negative 4, and 1. And if I add these up, 13 plus 4b, negative 4 minus b, and 1. And so if I wanted to write this as a polynomial, I would write x cubed plus negative 4 minus b x squared plus 13 plus 4b x minus 13b. And if I compare this expression with this expression, I can see that q is equal to negative 13b. And let's see, p is equal to 13 plus 4b, and negative 4 minus b is equal to 0, because there is no x squared term there, right? So that's going to be the key of solving this easily. Negative 4 minus b is equal to 0, so that means b is equal to negative 4. So we've already solved for b, and so that means that the blue coefficient, I can substitute negative 4 in there, and so I know that the b coefficient is actually positive 52, which means that q is positive 52. Okay? Q is positive 52. And the orange coefficient, 13 plus 4b, I can figure out what that is too. It's 13 minus 16, right? Because negative 4 times 4 is negative 16, which is equal to negative 3. Negative 3 is equal to p. So now I've figured out what p is and what q is and what the other root was. It's negative 4. So it says now to check your answer by using this expression here, okay? By solving for p and q using this. So let's put 2 minus 3i into our p expression. So I'm going to rewrite p. Instead of writing p and q, I'm going to put their actual values in there. So z cubed plus or minus 3p, minus 3z plus 52. So first thing I'm going to do is I'm going to substitute in 2 minus 3i here. And 2 minus 3i cubed, that's the binomial expansion. So I'm going to expand that. 1, 3, 3, 1. So it would be 1 times 2 cubed plus 2 squared, and then negative 3i, and then times 2 times negative 3i squared, and then the last one is going to be negative 3i cubed. So let's simplify this. So this will be 8. This will be negative 4 times 3 times 3. So it'll be 4 times 9, which is minus 36i. And then the next term is going to be 3 times 2, which is 6, times negative 3 times negative 3, which is 9, is 54. 54i squared, which is negative 54, 9i squared, negative 54. Okay, I think that's right. And then the last one is going to be negative 3 cubed is negative 27. I cubed is, I squared is negative 1, so I cubed is negative I. So let's combine those. We have 8 minus 54, that's negative 46. Negative 36 plus 27 is negative 9i. So that is the z cubed term. And then minus 3z would be negative 6, and minus 3 times minus 3 is plus 9, so plus 9i. That would be the z term, plus 52. So let's add those two together. We have minus 46 minus 9i, minus 6 plus 9i, plus 52. So, oh my gosh, that ends up being 0, right? Negative 9i plus 9i is 0. Negative 46 minus 6 is negative 52. Plus 52 is 0. So it worked. We checked it and it worked.